everything is new besides basically the base math and the base theory we use in the background. So let's start looking at what did we do and what was done in the last 1.5 years of development. On a high level, Multiscale Designer 2024.1 or Multiscale Designer X as our internal name is a brand new version of Multiscale Designer, fully redeveloped. We redeveloped and redesigned the GUI process, took everything out which was a bit cumbersome, made everything a bit more easier to let's say to provide you a much easier to use GUI and processes. We fully reorganized our back end. It's Python driven. It can be easily integrated into other solvers, into other technologies. Incorporated some new technologies and machine learning methods into the inverse processes. And for sure, something which is hardly ever visible, but we are constantly working on and improving, getting new features in, improving the QA, getting small errors out of our plugin, our connection to our macros, to the supported macroscale solver. What's the major scope of a 2024.1 release? So we want to perform the complete material model development, virtual test lab, and similar use cases for. We focus with that development on the two majorly used material types: continuous unidirectional reinforced materials and discontinuous fiber typical injection molding materials. We looked into the parametric unit cell library and took over what was heavily used and what's hasn't been heavily used, and we dropped a bit support here, but we enhanced the data structure behind the scene. We have, we reworked the linear and nonlinear forward development processes. One major part of the work in the back end was enabling OptiStruct to be used as back-end solver and for any virtual tests like unnotched tension compression, open hole tension compression, bending, rail shear, and dogbound. It was a cumbersome work together for OptiStruct team to get a lot of small tickets solved, but at the end we did it, and now we create OptiStruct models which can be copied and reused in the back end. We developed we kept it as a Windows desktop application for model development as virtual test lab. And for sure, we work on improving on the structural simulation and interfaces like OptiStruct, Radius, and Abacus. That was the major scope of that release. But let's jump directly into into the demo part. So I will show the two major processes. The first one will be the forward and inverse unidirectional material characterization, and I will give you an overview on the inverse short fiber reinforced, the new inverse short fiber reinforced process. Now, if you open the new Multiscale, you will see this changed initial window. You can choose between opening a new, load an existing, or you can load pre-existing examples. Right now we support a continuous unidirectional, discontinuous, and an initial woven template. Let's start creating a first unidirectional forward material. Let's call it demo forward. I choose the material class. I choose the matrix class, could be a metal or a polymer. I choose the fiber class. I choose my material subclass. Basically, that's my unit cell. That's the fiber honeycomb. I want to use the fiber honeycomb, and I hit OK. We changed a bit the logic of using the GUI. So first, you need to do all the model definition: microstructure, micromaterial, macrolaminate, and macrotest. And then you can do all the other analysis after you defined everything. So now let's start, for example, with a unit cell. You can choose your various inputs, manufacturing data or geometric data. In this case, whatever. Let's assume I have a 65% volume fraction. The number of threads can be reduced. I will go to the micromaterial definition. So let's start with the matrix system. So I will use a thermoset. Via import, you get access to our also pre-existing generic database. And let's take the standard modulus epoxy, dry and static. As you might have already seen in the background, all these curves are live updated. So you can see the physical parameters, linear parameters, and nonlinear in one place. We can plot also the plasticity parameters. If I change a parameter here, for example, I would go 420, you can see how the curves are changing. Initially it was 81. So all updates can be visualized, so you can check that your parameter set looks somehow reasonable. Same for the autotropic damage for sure. Let's go for the fiber and select the carbon fiber. In this case, I want the carbon fiber, and let's standard modulus is fine. Let's take the standard modulus fiber. Again, here we have the physical parameters, linear parameters, and the nonlinear parameters all in one. Now we move on with the macro definition. Since we know it's a unidirectional material, we predefined the needed 0, 90, and in-plane shear, symmetric 45 minus 45 layup. And we already predefined the minimum test set you need to run, and that's the longitudinal tension, longitudinal compression, transverse tension, transverse compression, and in-plane shear. But for sure, if you would like to add a laminate, you can do it. You simply increase the number here. If I want to, for example, create a symmetric quasi-iso, I could do 0, 45, 90, minus 45. Let's use a ply thickness 0 to 5. Didn't do it. Need to check that. Okay. Ply thickness. For sure, it can be added manually. I need to hit sync. Sorry. So I can add a macro test. So in this case, I would like to run the quasi-iso. You can take the standard parameters and take the new layup. Let me save it here. And now let's start with a forward linear. You see this summary of the test here. If I want to run this, I simply hit run. All 3 steps, which we before 3, is basically now all done in one batch run. We do the homogenization, we run the simulation, extract the results, write this MDS.dat file, and we can review the results here. And we added this nice review option, for example, here for the modulus with the different tests. You can review the torso ratio or the shear modulus. You can do that also only with selected ones, and you can compare a couple of results. Via export, that stuff can be exported to the CSV. If I go to HyperWorks, we visualize the unit cell with the 6 unit load cases. If I'm happy with these results, as you can see, the modulus, torso ratio, and shear modulus, I can run my forward nonlinear simulations. For example, I only want to run the basic 5. I hit run. We run the nonlinear tests in the background. All done. Now we can start reviewing the results. For example, first looking at the overall summary. I can take, for example, this tension out. We see the shear dominated and the transverse compression. You see the summary of the modulus and the strength and the curves down here. Again, you can export all these data as a summary CSV and directly the MDS.dat file. If you want to have a closer look, for example, what's happening in my longitudinal tension, you go to this new tab, forward nonlinear state variable. I activate my scaled macro stress strain curve. And now, for example, I would like to plot what are my damage variables doing. So you can see the curve over here. You see that the fiber damage, that's that one here, that color code here goes up to 0.5 while we are going down. There's the matrix. Matrix is untouched. Let's say the matrix isn't there. There's the matrix isn't damaged at all in the longitudinal tension. We can review the same, for example, with the transverse tension. And here we can see that the damage is, we have a damage in the matrix and the fiber, so we enable this review of state variables, so combined with a scaled macro stress strain curve to, let's say, to get a better understanding what's happening in the material. If you're happy with these results, you need to, let's say, you need to move on to your structural simulation. We reworked also this export. So on top of the homogenized, for sure, we have this multiscale export. We provide the summary list of the state variables of the material model with IDs. And to export the MDS.dat file, you only need to hit export here and choose the file location. One thing with the radius export, which was always a bit cumbersome, was collecting the state variables for let's say, if you wanted to add the element deletion to the MUD MDS in radius. Now you get this list directly here, export the MUD MDS, and together with that list, you know exactly how to define the element deletion. And together, say with the abacus, you can activate the output. You activate the output into the ODB here. You select the abacus version and all necessary files will be exported. That's the new interface. So once you're happy here, you can also add your virtual test. For example, we take a open hole tension. We have some default parameters. Once you run that thing here, we will create the OptiStruct model with all the proper boundary conditions. Proper runnable in the background, run OptiStruct in the background and extract the results. That's the new forward process. So no more Excel integration to review curves, all in one shot, live update and review of the micro material curves. And these specific workflows with good default values for continuous fiber and short fiber, where we know exactly what you need to do. Now let's have a look at the rework of let's have a look at the rework of an inverse process. So let me open this unidirectional demo within our examples to do that. If you work with that unidirectional inverse, it was generally working pretty fine, but it was always a bit cumbersome to review results, check the results, and compare the results. And also one major pain point was that you needed to calculate by hand these brittle damage parameters. And we optimized the ductile instead of doing all in one shot. And what we did, we enabled with optimization of all nonlinear parameters in one shot, brittle, damage, and ductile. And you can easily review the optimized results. Now let's have a look how that GUI works. We defined everything here. I have my microstructure, my material, my typical macrolaminate and microtest. And now let's start with the inverse linear. We know which tests need to be run. So longitudinal tension, longitudinal compression, transverse tension, transverse compression, and in-plane shear. We already know which material parameter on microscale need to be optimized to fit these curves. That's something fixed here. The only thing you as a user need to do, you need to type in the deterministic mean value out of your test campaign into that row here. These upper and lower bounds for these micromechanical values are automatically calculated for the initial step. If the optimized result is outside of these bounds, you will anyway get the result, even if it's outside, and we will get that information here. So let me run first the inverse linear. So I know that's my goal. I know these were that's the bounds of my initial parameters. I'm switching to a result review. You have, let's say, this tabular view here, the simulated value, expected value, and the error in percent. The same for all these 5 tests. At the same time, we can review that also with this nice diagram here, and we can see the updated parameters over here. If you like that result, you can export it as CSV. I update my micromaterial database and save it. And now let's move on to the inverse nonlinear fit. For each test, you can define 2 sets of variables. First, the elastic and brittle damage parameters. That's that thing here. So you define the modulus, the ultimate strength, and the ultimate strain. For any brittle damage, that's enough. So, for example, the longitudinal tension, we can assume the material is brittle to the point of failure. I know the modulus, I know the ultimate strain, and I know the ultimate strength. And that's predefined. We know which microscale parameter corresponds to that curve. We do the same for the longitudinal compression. We do the same for the transverse tension, brittle matrix damage. If we want to optimize ductile parameters, here in tension and compression, you can also import your measured stress strain curve here. In that case, we optimize. At the same time, we optimize. We try to find the closest fit to that curve. So in one GUI, you define the measured brittle, measured ductile, the curve behavior, and all is optimized in one shot. And we know exactly which parameters are influencing which curve, and that's the predefined set of parameters you can see down here. So, for example, for the matrix ductile, we have this exponent for the evolution of the plasticity curve, ultimate strength, and the remaining slope and after full plasticity. The Drucker-Prager beta parameter, if you have also the 90-degree compression, which measures the plasticity under compression. And we have the 3 brittle material parameters. I'm hitting save. Now we optimize all these 5 at the same time. And you get the optimized parameter set for brittle and ductile at the same time in the new inverse process. If we try to remove all unnecessary input of parameters, we know exactly what they are, and the user shouldn't change anyway. Simplify it, try to simplify the workflow, do it straightforward. See, if now we are done with the job. Now we can go to the inverse. We can compare the curves, so longitudinal tension. These are actually 2 curves. They're only exactly the same. Same here. Here we have a small difference. Again here, this fit is exact as it looks like, and that's data from NCAMP which we are fitting. So it's not any fake set of data. We have a fit of the data. We have a summary of the optimized parameters down here. I hit update material, and we are done. If you look at our older trainings, how much Excel sheets and calculations you needed to do all these fits, it's a massive improvement, let's say, and much less error prone compared to the old process. Okay, that's the uni. Now let's have a look at the new short fiber reinforced process. We have a similar template, but we decided to fully rework the inverse characterization. Why? Because that's something I try to summarize here. In opposite to continuous fiber reinforced, we have a strong influence of the elastic and inelastic parameters, and let's say of elastic parameters on the inelastic behavior, which we don't have, let's say, with the continuous fiber. So if I change the modulus of the matrix down here, It will change a lot, again, the behavior of a material further down in the plasticity. So looking at that, we decide to rework the short fiber inverse characterization, because with the short fiber material has a high influence of elastic parameters on the necessary inelastic parameters, and also some geometric parameters on the unit cell to find the optimal fit against the measured curve, and optimizing, let's say, only elastic first and find the best fit, and then go into the inelastic regime. Sure, let's say we saw is not the best way to approach the problem. So that's why we switch to this, to the combined inverse characterization. So we are optimizing at the same time elastic and inelastic material parameters, and we are optimizing one geometric parameter of a unit cell, and that's this end gap ratio, to find the optimal fit. So that's, since the material behaves different, and also let's say, compared to a continuous fiber, we need to use a different method compared to a continuous fiber to optimize the material. To show you that process, let me again open a new pros file, and I will go to this injection molded inverse example. The injection molded template provides the same, let's say, infinite selection of correct microstructure and the material, needed layups to test the material, and the necessary macro tests. In my case, I'm having some measured FOTs together, let's say, together with the test curve. And if we go to this inverse combined process, all you need to do, you need to import your measured stress strain curve, average measured stress strain curve, provide the elastic modulus for the 0 and 90 curve, which we want to simulate. We are optimizing at the same time one geometric parameter, the matrix elastic parameter, the yield strength, and three ductile parameters of our matrix material. Now let's save it here and run it, and run the optimization and see where we get. Again, here we can check that our input data is generally working good, so that the initial slope is matching with our test curve, which is always the first sign of the sanity of my input data. And we run our inverse optimization. If you work with that process, like we always had this, communication that this end gap ratio should be somewhere between 3 and 8%. I used this inverse process on a couple of data sets, and I could find a lot better fit to the measured data with higher end gap ratio, something above 10%, between 10 and 15%. So there seems to be some a solution also, let's say, with higher end gap ratios, which we didn't look at because, let's say, we simply didn't use that variant before. At the same time, we see that this optimization is close to be ready, and we can review these results and see that also the combined inverse optimization process for the short fiber reinforced is working pretty smoothly. While that one is running, I still have the old results here. So what would be the expected outcome? We have our optimized material parameters here. We see our optimized curves on the right-hand side, and that's the result we will obtain. That was the overview on the new version. In between, he finished that result. So we saw that we got very similar results.